Zabzine to tell us about gauge theories, diagrammatics, and algebra. Okay, first of all, thanks to the organizers for inviting me. I have no idea why I'm here, but let's enjoy it indoors. So, I decided to give a rather general talk. It's definitely related to topology. I don't know if it's related to number theory, but gauge theory. So basically, my idea that I will discuss for you gauge theory. My main example will be this magic Chern-Simons theorem. But I will concentrate on sort of challenges and algebraic properties of perturbation theory. And again, I will assume that you have no idea what I'm talking about, so I will be very, very basic, but I will try to explain to you what algebraic features are. But actually, a lot of algebraic features which people found experimentally, they're true not only for Chern-Simons, they're true for many, many theories. So let me give you a crash course on perturbation theory. You have no idea what it is, but let's be brave. So typically what we need to calculate, with you some integral in n dimensions. And let's say our integral has this form. It's finite dimensional integral bij xi xj. Right? I mean, that's integral you know how to take. But then you will add something, put g over 3 factorial. Then I will write something like vi, vj, vk, psi, xj, xk. And again, as a physicist, I assume that whenever the index is repeating, this is summation. And this is integral uncalculable, but what you are doing basically, you just expand this guy, right? So you would expand this guy in, I don't know, s from 0 to infinity. Then you will have gs s factorial, and then under the integral, have something like this v. Let me write shorthand like this in power k, and then minus 1 over 2 vij xi xj. Okay. So in principle now, these integrals you have to take, it's just, these integrals have the following form, right? So now I just have to learn how to take these integrals, n xi1 up to xil e minus 1 over 2 b ij xi xj. So this integral, it will be some stupid factor with some whatever 2 pi n over 2 determinants of b. Of course, I assume that my matrix B is invertible. So there exists B inverse. But then what you have to do, you can basically create a diagrammatical rule for this. And this is what physicists are doing. You just look at these L points, okay? And then basically you have to create pairwise things, for example, like this, like this, like this. So this would be, for example, I1, I2, 3, etc. And then for every picture, you have to write here correspondingly B inverses. So for example, BI, if it's BI4, BI1, I4, etc. So then you will basically have a picture of all this pairwise connection. So this goes under the name of Wick theorem. So now if you combine this prescription, again, if you have no idea, this is very easy to prove. It's just fun. And typically this is why whatever physicists are doing are typically related to enumerative geometry. If you start to play with integrals, for example, counting of different graphs with different properties can be reduced to integrals. So anyhow, what now you are doing is, so I basically have to contract the things pairwise. So all these things can be eventually packed up in the following things that I have to sum over graphs. And then I will have G in some power of S. Then eventually what I will have some object here constructed for the graph, then if you normalize things properly, they will be automorphisms of the graph, but my graph will be all, for example, trivalent graphs. So for example, one of the simplest example would be something like this. So for example, if I start to look at order s equal 2, so obviously you can figure out that in these things, I have a trivalent graphs, I have to contract them as will be only even. It doesn't work otherwise. Yep.
So the first integral doesn't make sense. I mean,
This integral.
Does that converge? Because we...
That's a good question. Of course, it does not converge. Quite often we don't care. So what we are doing, we are producing asymptotic expansion. That's the best we can do.
But yeah, the second, does that converge if you assume that Bij is positive definite?
Yeah, that's convergent, right?
Okay, so
right, you're absolutely correct. So typically there is a whole this industry also you can study. So this is a way of producing asymptotic expansion. And then you can ask all these questions if this asymptotic expansion can be, I mean, if by knowing asymptotic expansion, you recall the actual function if it's well defined. It's a separate thing. So right now what we are doing is we are doing things pretty formally, and we just basically have integrals, and then we convert to some diagrammatic things that it's very algorithmic. So for example, when I have s equal 2, so I have only two ways of constructing things, for example, like this or like this. And then for this, I will write, just let me be explicit for once, I will write B1, 2, 3, J1, J2, J3, and then I will write something BI1, J2, J1, BI2, J2, BI3, J3. Okay, so this is just a rule. So every edge, I have what physicists call propagator. Then the vertex is this guys, and the diagram will just tell me how I'm doing. And again, there is different normalization. So if you, for mathematicians, whoever wants to know about this stuff, there are very wonderful lectures by Pavel Ettingov at MIT. I mean, specifically for mathematicians. So if you, I mean, you have to put these factors correctly, then here will be very nice thing. So this is exactly what I will call F gamma. So basically what I'm saying to you that if I take this integral and then I can write as an infinite sum of trivalent graph. So for example, this is a graph which has only trivalent vertices, no external edges, etc., etc. You sum up. Now, of course, I mean, it's uncalculable things you can calculate at the beginning, but of course, the number of graphs grows, asymptotically, etc. Of course, what you can do, you can upgrade these calculations to different things. So, for example, just to give you another example, you can look at x1, let's say x2, xi3, xi4, and then you want to calculate this integral. Again, let me write for shorthand, it's obvious what I'm doing. And again, you want to just produce some asymptotic expansion. Yes, X.
So this summation is over which graphs?
So this is summation over trivalent graphs without external edges. This is, and so this is, for example, in the theory. So this is actually what Chern-Simons will correspond. So this is called typically vacuum diagrams or vacuum graphs. So, for example, why all these manipulations are extremely nice in enumeration theory, because if you cook up a good theory, whatever, you can put more vertices. I mean, here you get some counting, and here you get integrals, which you can calculate by other means. That's why, physicists all love enumerative theory secretly. So, for example, here I have to again expand like this, etc., but I have these external guys. So, for example, the diagrams here will have external things. So, for example, I will have I1, I2, I3, I4. And then if I want to look at this coupling at order 2, so at G square, right, I have to write to you all possible ways I can connect, and I will have these guys. So, for example, I will have this, then I will have this guy, and then I will finally have these guys. And etc. But again, the problem is that complexity, once you start to go to high order, complexity grows very, very fast. Okay, now, this is a standard perturbation theory. And what we are doing when we go into this magic world quantum field theory, basically you do things the same way, only these guys happen to be not finite dimensional operators, linear operators, but infinite dimensional. So for example, that can be Laplacian. And then you have to invert this Laplacian in the appropriate way. You can do it. And then your sums here get just replaced by integrals. So, and then you have to see if your expressions are well defined. But in finite dimensions, basically, in quantum field theory, what you are doing, you just sending this number and to infinity in appropriate sense. And of course, you know, when you replace the sums by integrals, etc., there are sometimes a lot of troubles appear, but that's I'm not going to discuss. Sometimes you know how to resolve this trouble, sometimes not, etc. But for example, when you stay in lower dimensions, typically 2-3 dimensions, there are no problems. I mean, for example, if you start to write this with Laplacian, there will be no problem to define these integrals, and they will be reasonably convergent, and people can discuss it. And you know, okay. Any questions about perturbation theory? Right. Now the question is, what's you know, basically what I'm telling you that in normal field theory and normal perturbation theory, you have an operator B, which is, you know, linear guy. It's invertible, and then you have these vertices, and everything can be written as some contraction of inverse of B with these vertices. Okay. Now, what's a gauge theory and what we are talking about? So gauge theory is basically, it's the following phenomena, which gauge theory. It's when B, so we don't have inverse of B. So B basically has a kernel. So if B has a kernel, we have no idea how to perform perturbation theory. So let me give you right away example. And again, now I'm switching to more interesting things. So let's talk about Chern-Simons from this point of view. So in principle, what Chern-Simons is that we have some three manifold, then we would have some Lie algebra, Lie group. And then I will write to you this famous Chern-Simons okay, which would be, for example, let's assume that it's some semi-simple, nice Lie algebra. So I will write to you something like this, 2/3 A cube. So A, again, it's a connection, but I just, for the sake of discussion, I will assume that this is just a one form, the algebra valued one form. Now I mean, unfortunately, what I raised to you that what we would like to do, right? We would like to write something and calculate, for example, put here whatever Chern-Simons section. And naive thing would be just exactly this treats as vertex, and this is perturbation, as this is our S operator B. And then we have to expand in trivalent graphs, and then we will get some answer. The problem is you can complain right away that B is not invertible. Right. So actually, it's not invertible, and it's actually related that this function has a symmetry. So if you transform, for example, So epsilon is just zero valued form in Lie algebra. So these two facts actually goes together. The fact that you have a symmetry of this guy, this is typically called gauge symmetry, and the thing is that D is not invertible. So what you have to do, there is a prescription, and this is why it's interesting. That's what I will discuss with the diagrammatics. You cannot invert DRAM differential on differential forms, but you can invert on certain subspace. Right? So D does not have inverse, so we know that we cannot invert D. Inverse, it doesn't make sense on differential forms because it has a huge kernel. But what we can do, we can invert this on subspace. So again, actually, I will talk in a moment. You have to put full complex DRAM complex here in the game to make sense. But for the moment, let's just relax it. Let's forget it. So for example, I can invert it on the kernel of the Dagger operator. So again, it's a choice. So if I invert it, I will typically just get some type of green function. So what I will solve some equation, you know, zeta prime equal to delta of zeta prime. And again, I'm saying is that I will not be able to make sense on all differential forms. So I have to restrict on some subspace. Okay. And then, you know, what I have to do, I have to, let's say I'm doing the things, and then my perturbation theory start to look as follows. So again, this theory is very similar to example I was showing you. So I have trivalent graphs, and I have in some reasonable sense the inverse of this operator. Then what I will get some sum of trivalent graphs. Then I will get something which I will call B gamma and something which I will call C gamma. Again, there are some physics ways of getting it, but sort of don't care about this very much because what for us would be interested is the final answer and what property it has. So whenever you calculate, things are factorizing here. So C gamma, this is what will be related to Lie algebra. And again, for me, what I will assume, so my Lie algebra, I will have my structure constants. I will have invariant metric. And physicist, I like to write indices. So these guys will be the following. So you take a graph, you construct according to the graph, right? So for example, for every trivalent vertex, this would be a vertex, and this would be my, what I will call propagator. So for example, if I want to take this gamma and construct, I will just write FA1, A2, A3. F of B1, B2, B3, and then I will just B1, B1, eta A2, B2, A3, B3, right? So I'm just using structure constant, I will get a number. Okay. Then, you know, you can play a lot and then you construct according to, so for any trivalent graphs, I don't know, you can have more fun. It's the homework for the brave ones. For example, you can calculate number, I don't know, for this graph, SU2, etc. So you get a lot of numbers. So the data is Lie algebra, this invariant symmetric pairing. And then you can construct these numbers. Now, what about these numbers? So these numbers very easy to construct, and of course you can do it by hand for simple example. So you can put on computer and everything is easy. These numbers you can know very easily. Now, B gammas, this is a complicated thing because B gammas, it's basically this integral. So this is what in physics people call kinematic data. So you have to basically take, according to this graph, for example, you will have two integrals. You have to take this function in a cube because you have three propagators. And then instead of sum, you just integrate over these guys. Now, there are some issues, but for Chern-Simons, they can be resolved because you can ask if this integral is well defined. But people studied this in 80s, and actually you can sort of, there will be some problems on diagonal, but you can resolve them, compactify these things, etc. So it can be made sense. So this is also another number you get.
These are independent of the Lie group.
Yes, it's independent of Lie group. So this number depends basically on the following data. I want to invert DRAM on appropriate space. And then I have to find these green functions, and then I have to perform these integrals. So it's a crazy complicated problem, especially on a, yes.
Sorry, I missed this. What is K? The Chern-Simons action?
Okay, it's typically called a level. It's typically quantized. I don't want to go and discuss the things very long, but it's a number, it's a parameter of the theory you can put in front. It's roughly like a couplet, etc.
It's a complex number or
Integer.
integer?
It's an integer. For non-compact groups, it can be complex.
I see. But okay, but then the Feynman integral, I've usually seen it with an I. So here there's no I. Okay.
You're getting picky. I mean,
I'm sorry, no,
it's okay. No, of course, there is I, there is K, there is a discussion, these things. So this, for example, K, however, I will mention when you go to the not polynomials, etc. So typically there will be these relations of whatever 2 pi I over K plus whatever dual cosetter number for the thing. So something like this. Typically, whenever you calculate in Chern-Simons, for example, you take a node, you have to insert here a certain object which corresponds to holonomy. You can calculate, etc., etc. So typically, this theory is defined, but the way I'm telling you, you never calculate the answer. What you are doing is basically this is what Witten realized. You have a theory, you just believe that it's well defined, and then you have to understand how it works on the different cutting, gluing, etc. You create these axioms, which goes on the name tensor modular category. And then, basically by applying this finite number of operations, you can construct everything, okay? You can actually do it. It's extremely successful thing. Then I'm telling you, let's go painful way, okay? But I will tell you in a moment why it's interesting. Yes.
I just have one more silly question. So over here you write D and not Laplacian, and that's a first order operator versus second order operator. Does that cause any?
No, it does not call. I mean, in principle, you can write any operator, any linear operator, as long as you can invert it.
It doesn't need to be self-adjoint.
No.
Anything like that.
You have to, basically what you have to discuss on different fields, some operators better. If you, for example, start to look at, spinorial fields, for example. So basically you would like that something staying here, it's secretly related to elliptic complex. I mean, then things, would make sense. So I'm skipping a lot of details. Okay. So, but what we are doing is we are doing this with the graphs. And so now, basically, for example, if I would take for you and calculate, so let me call this magic object, for example, for S3, I mean, written in end of 80s, I mean, you can calculate concrete expression, which depends on the algebra data, etc. And then you can calculate, for example, there are closed expression for deciphered manifolds. Now, these numbers you basically don't know. These numbers you know, this you know, maybe a few diagrams and that's all, and it doesn't work. However, especially just let me tell you where it lies in terms of invariance, etc. At the same time, if I start to expand in this coupling GS, then actually these integrals sort of have, so these graphs organize in the finite number of things. So if I look at number of my vertices, then I write all diagrams, and it also should give me invariance. So typically this invariance, I'm very schematic. They will be called finite type invariance. So for example, if I will do nodes, so for nodes, I'm not going to discuss it, but the diagrams, you have to do the what's called wheel diagram. So you have a wheel, thing starts there, and then you go here. So for example, you can collect all diagrams with a finite number of vertices, sum them up for the node, and this is supposed to give you a finite type of invariant for the node. Uncalculable, too complicated simple. So Kontsevich defined them as integrals, but it's very hard to calculate. Okay, good. So now, what do we want from this? However, what people started to realize slowly, right? Let me just explain to you. Imagine, right? I put for you some non-unique data here, right? To define d-dagger, I have to introduce a metric, right? And then what people told us, whatever, 40 years ago, that this combination should give me some topological invariant, for example. So it cannot be depend on this subspace. In principle, I should be able to change the subspace, and then this number should not change. So actually, this is a, if you wish, gauge invariant. So what happens is the following: that if I take B gamma and I change it somehow. So for example, I can change this by changing the metric, right? If I change the metric, my d-dagger changes, my kernel of d-dagger changes. So I will get a totally different Green function. But the statement is of gauge invariance, then my numbers B gamma changes. But what will happen is that this guy should not change. So what should happen is that so actually, sorry, just so this combination basically over gamma should be 0. Okay. Now, so what's about C gamma? So C gamma actually satisfy a lot of properties. So, right, so imagine is that I write for you these graphs, right? So let me start for you to give some examples. So imagine I write a big graph and I have this collection of subgraphs. Then, so let me call it S diagram. Then I will have this T diagram. And then I will have this, what physicists call. So imagine this is a bigger diagram, but I look it up. But if I start just to look here, so for example, for me, if I concentrate on this CS factor, let me just pull A, B, C, D, right? So this, if I ignore everything else, this will look as something like F of A, B, L, F of L, C. So again, raising flowering indices, I'm using my invariant metric. So what you can basically convince yourself that if I start to look at these diagrams and construct them, so this is A, B, C, D. So of course, what you can convince yourself that if I write for these diagrams analogous guy, again, the diagram just tells me how to construct indices, and for every vertex I have a structure constants. Of course, I have this relation, which is nothing more than just Jacobi identity.
You're not claiming that these are all the graphs, right? These are just the three relevant for some discussion.
Yeah, I'm looking at trivalent graphs, and for example, now I'm assuming that this is sort of part of a bigger graph, and that's all. Yeah. So the story is more complicated, but in all this story, actually, so there are two statements just to keep in mind. Any reasonable physical theories, it can be recovered to Chern-Simons, and any diagrammatics can be made in terms of trivalent graphs.
But I just even trivalent, just to like make a dumb example, the nice one with the crossing. If your little leg was horizontal above. This to me looks like a different trivalent graph.
These are three different trivalent graphs. Right?
Yeah, but I think like there's maybe a fourth different trivalent, like, so you don't care about.
No, I don't think so, no.
You have to separate the four into two pairs, so there are three ways of doing it.
Ah, okay, so there is some other, it's not just any trivalent.
So I keep this as external labeling. And basically, so now I'm saying is when I'm writing these numbers, I will have something like this, which is nothing but just Jacobi identity. So basically, what's going on here is that these guys satisfy very concrete properties, basically this sort of Jacobi type of identities on these numbers encoded in the graphs. And then B gammas can be changed. And, you have to basically invent some way of calculating B gamma in such a way that this together with C gamma is 0. And also if you start to sort of play with the things, this should vanish class by class in the graphs, depending on the number of vertices. So in principle, there are these games, and I don't know, we played like whatever 10, 15 years ago. You can start to construct totally different theories. It's becoming complicated thing, but in principle, you can try to invent not related to Durham differential, but basically if I have any other DGA or whatever, I can try to play these games if it's finite dimensional, not differential forms, if there is triangulation, etc. I mean, these games are very complicated. You can produce some, of course, theories with perturbation theory formulae, but they do not bring any interesting topological information. I think with triangulations, it only works for Riemann surfaces. This program has been done, I think, by Pavel Mnev, but otherwise it's getting too complicated. But this type of things you can in principle play. So DRAM, whatever this part, you can try to start to replace by different things. So basically what you need some DGA with some measure and some notion of D-dagger, which is of course not canonical, and then you can start to play and you can construct very easily some simple example. Okay, now let me try to explain to what people have realized in physics experimentally. So I will talk not only about Chern-Simons. This is actually a feature of all gauge theories. Okay, so let me concentrate on these diagrams. So quite often, if you take, for example, these diagrams and just look that this is, guys, some external states, then what you can write, so your typically people call this amplitude, will be organized something like this. So for physical theory, this might depend on some moment, on some another data. For example, imagine you in R4, you have your gauge field or whatever. You can just pick up some basis, I don't know, plane waves, whatever, decompose, and you will have something. For example, you can label this by momenta, by coordinate. So if you start to write your diagrammatics rules, so like here, you will get again, we'll of course always have the scalar factors. And then if you have external legs, you basically will have some extra data which specify this external legs. So roughly speaking, you will have some function of your momenta in S, and then you will have S, and then typically you will have this guy ds. So this is typically will be some analog of inverse Laplace operator, and this can be some momentum guys, etc. So it varies from theory to theory. What's important that this structure for any gauge theory always persists. The only thing is that these guys can be more complicated. If you have external states, basically the labeling of external states goes here. And then I will have something like this. and t of ct dt plus and u of cu du. Okay. So I'm not specifying these numbers, etc., but that's how it will look like typically. Now, when I talk about this type of invariants, for example, it's actually very easy to see what's going on. So by these guys, so if I call them ni, so if I shift ni by ni plus arbitrary object di, right? So what you can observe is that my A4 will be shifted by the following. So it will be in A4, and then this is organized in such a way that I will have, so this di is cancel, and I will get plus alpha s st plus. So this is example, I mean, type of shifts you can do. And of course, this is by Jacobi 0, so this is 0. Alpha is whatever.
Sorry, could you remind me what N and D are?
I don't want to, I basically trying to tell you that roughly speaking, D is like P square, or, I mean, it's in momentum representations, Laplace inverse, for example. And N's are just some function of momenta. So typically, I would assume that if I associate here one form, it would have a Lie algebra indices mu. For example, in flat space, I go to momentum representations, I can write something like this. I don't have to go to momentum representations, but basically, don't think what these objects are. I'm just trying to give you that these objects are not unique by definition. So it's some objects you calculate, it's I mean, done sort of complicated way, but what's important thing that when you start to look at gauge invariance, so what it means is that this object can be changed always by this, because by Jacobi, these things does not change, okay? And then there is, people realized very funny experimental fact. I think there is a whole industry on this physics community, is the following stuff. So there is actually, so this is goes under the name color kinematic duality. So it's experimental fact. So you do a lot of calculation, different theories, for example, and what you realize that there exists a choice. So there exists a choice. So there's some choice of these guys in such a way that these objects satisfy basically this Jacobi type of identity. No failure. So people, I don't know, look at Young Mills or look at three-dimensional Young Mills, four-dimensional Young Mills. It's very hard to calculate those numbers, but when you start to calculate them, there are totally different techniques people using. And of course, I'm writing for simple diagrams. You can sort of what I'm telling you repeat for different diagrams. Basically, the idea is the following, that if you try to basically split your diagram, so again, you write something like this C gamma. So then you basically have to factorize some factors related to Laplace inverse them. Then there is some numbers here which would basically satisfy the same type of Jacobi identities. At least there exists a choice of such numbers. So people were always able to choose, and it's a sort of interesting fact which we will discuss in a moment. Okay.
I don't understand the statement. Is the choice of what? Of the NIs?
Yes.
The NIs are
Complicated objects you calculate from whatever momenta, some data. I will try to give you a more geometrical meaning of this, but basically what I'm trying to say the following thing, that you go to whatever theory you take. You specify your data, states, etc. Complicated. Theory can be different. Then whenever in gauge theories you do diagrammatics, there is always this factorization between color and kinematics. So always something for the color, something for kinematics. Then what people realize that if you look at kinematic facts, they're not uniquely defined, right? So you can always shift them by some, they have ambiguities, but you always can basically make some clever choice that these guys satisfy Jacobi-like identities. Okay. So people started, that's why it's called color kinematics, because when color satisfies Jacobi, it's obvious. But then when you do totally different calculation, then this becomes sort of strange. Okay.
Can you say what the physics name for the N is?
Hmm?
What's the physics word for N?
This is just kinematic factors. The only thing you have to factor out this p squared. I don't know what's exactly people. No, they don't have a physical. I mean, that's why it's a bit strange. So calculation of people, I mean, like it, but it never reached math community because it's very hard to formulate, because you do some black magic, you do calculation, you extract some factors, and then you get this stuff. But for example, let me tell you even more amazing fact is the following, that so if you have these diagrams, so this is whoever likes physics, it's more black magic. Okay, so you have this sort of object C gamma, and that's D gamma. Okay, so this is very canonical object D gamma. You take a gauge theory, your favorite gauge theory, and you calculate, and then you take a choice N gamma, which would satisfy relations like this. Then out of blue, you just construct another object, N gamma over D gamma. And then you find that this guy is actually, if it's a gauge theory, then there is always exists some gravity theory. This is typically called double copy. Again, it's experimental facts. It's a lot of diagrams. People just calculate. There is a whole industry. I don't want to go there, but if you make these choices, so this is actually works when this and gamma satisfy the algebra relations. If you just copy them and strip off color factor and you write like this, it starts to coincide with some gravity perturbation theory. There is a list. So you do calculation here, you can map here. Okay. Yeah.
By experimental fact, like, is there some experiment that's
No, so we are math conference. Experiments mean that it's not you run experiments, you do a calculation, right? So basically, I think I'm referring what Arnold used to call experimental mathematics, right? You're not proving a theorem, you just take a diagram, concrete theorem, and you start to calculate, okay? And then you realize, you factorize the things, you realize that you can make this choice, and then you do totally different calculation, totally different things, and then you realize this sort of double property. So in this sense, experimental. We don't have any proper understanding of this fact. Yeah.
When you say exist, can you quantify, like, are there many or choices you can make usually, or?
I think typically what people do, they just write your whatever amplitude, they know which ambiguities, I mean, there are, and then they always basically give you either recipe that it exists, or in concrete diagrams, find the concrete choice, etc. We don't know by which things it's, controlled, etc. Of course, it's a cohomological problem. Okay. Good. So now let me start to explain for you this stuff, at least for Chern-Simons theory. And so I first will a bit outline flat case, and then I will do invariant statement, and then this is basically hopefully true in more general cases, but simply get more complicated. So let's just, for the moment, consider R4, sorry, R3. Okay, so just for simplicity. And then I would have my theory, right? So my Chern-Simons theory was K over 4 pi raise of ADA plus 3A cubed. Okay. Now I told you that I cannot, so in a way, I'm going to tell you a very simple calculation, but people didn't bother to do it. So let me assume I want to evaluate this section on the some subspace, right? I know that my D is not invertible, so let me choose A to be in the kernel of the dagger. So it's a calculation which you can actually do very easily. Right? So how do I evaluate on the kernel of the dagger? I will give you, if you're worried about invariant statements on the general stream manifold, I will give you in a moment. But let's just do a stupid calculation like one would do in calculus. So D dagger, you remember, on the flat space, it will be something like this, right? So this is D dagger acting on A. So I have to write for you A in D dagger. So what I can do, I will just write for you in momentum representation. So D3P IPX. And then I will have something like this. So I'm using this Levi-Civita index mu nu rho, P nu psi rho over P. Right. So P is momentum. If I hit this by derivative, so if I hit with this guy, I will just produce P here, and this is Levi-Civita index contracted. So this is definitely will solve the constraint, right? So it's a parameterization. Of course, this guy is not uniquely defined, but I can write this thing. So then you can do funny calculation. You just take these guys and evaluate Chern-Simons. So what we are doing is we evaluating Chern-Simons on these guys. And then let me write for you the answer. So the answer will look as follows. So I will have D3P. Then here I will have psi mu. So of course I will have a trace, etc. So psi nu minus P, then there will be P squared mu P. So I will just introduce a shorthand notation here. So you do this calculation, then you will get this term. So let me do symbolically P1, D3, P2, D3, P4. Then you will have some psi1, mu1, psi2, mu2, psi3, mu3, depending on P1, P2, P3. And then you will get here some object, which you have to just with mu1, mu2, mu3, depending on P's. This is calculation you do yourself. So what I'm doing is I'm just taking these guys, plug it in, I have to evaluate, etc. So the question is, you can ask what these guys are. So actually you can do something else, another calculation, which is, we can calculate the algebra of volume preserving diffeomorphisms.
P1 plus P2 plus P3 equals 0.
No. So there will be delta function here standing inside of F. So what you can do, another calculation, which is very, very simple. So let me take for you. Right. So let me take for you this differential operator. This is the generators of, at least on flat space, it's the generators of volume preserving diffeomorphisms. It's a Lie algebra of volume preserving diffeomorphisms. So if you start to calculate this algebra, P1, L nu P2, what you will get here, you will get F mu nu rho P1, P2, P3. Then you will get L row of P3. Basically, these objects are this object staying here. So what if I do this gauge fixing again? It's a bit elementary, but sort of was overlooked. And in a way, this is a choice I can make for Chern-Simons. Of course, it's much more interesting for other theories. But basically what I'm telling you that if I'm doing the things, my Chern-Simons and these representations, the only thing is it looks very nice. I mean, this is why I have this one P square. So basically what I'm telling you that in momenta, I will have to, so I will have a color indices which I suppressed. So I have it, of course, trace here in the algebra. But then another group which I have, it's volume preserving diffeomorphisms. So I'm basically can tell you that if I would know this diagram, again, it's sort of too trivial case. Us three, we are not interested very much, but in principle, what I will know about this diagram, I know how to construct C gamma. But I also will know how to construct these guys if I start to construct this structure constants, which is of course structure constant for infinite dimensional algebra. And that's basically what's responsible for these things. Again, I like to do momenta, but let me try to give you a better explanation for this. Any questions? So, yeah.
So if you contract those, do you get the thing that is frequently called n sub gamma? Yes.
Yes, so
I see.
if exactly. So I will get n sub gamma, roughly speaking, there will be some p square. The only problem here, it does not look exactly perfect. So this is analog of invariant metric. This is f, and then I will have this p actual here, which is related basically in momentum representation to Laplacian. So let me try to, I know for most people this is horrible and this is more horrible. So let's make this simple statement in a fancy words, okay? So what I ignore for you, then in principle, when you write Chern-Simons, you do this description. I mean, you choose the kernel of the dagger, etc. So Chern-Simons, as you maybe heard, maybe heard the words ghosts, etc. So Chern-Simons, in principle, if you calculate loops, etc., it has many more fields. So actually, the proper way of formulating Chern-Simons is that we have a full Dirac complex. And then in principle, what I'm doing is I will have this, I can put them in superfields, 0 form, 1 form, 2 form, plus 3 form, have my DGA, okay? And then in principle, the full Chern-Simon theory with all fields will look like exactly, so you have the full integral over differential forms, and then you will write these guys. Of course, I will have a trace and the algebra, etc. And then what you are doing is, if you want to do it properly, what you have to do when you invert these operators, you have to pick up some subspace here, which is will be basically isotropic with respect to this pairing. And if you choose in such a way cleverly, then you will get here, invertible with guys, etc. So there exists a prescription, but important thing that you have to put all forms, and if you do it, then some of these fields actually will appear. This is typically ghosts. From this guy, you have anti-ghosts. I mean, this you guys set to 0, etc. So this is what's going on. So now when you choose here some subspaces, I told you, you need to invert deep appropriate. So of course, if we have a metric, we can put a d-dagger. So we have a d-dagger. Right, so D is a derivation, the dagger is not derivation, right? Anyone knows about the dagger, something nice. What's a failure of the dagger of in the derivation? Anyone knows? So let's just take two guys and construct its failure to be a derivation, right? So I take the dagger of A, B minus the dagger of A, B, and then plus A, the dagger B, right? So if it would be a derivation, this would be 0, but it's not a derivation. So it's actually a Lie bracket, Lie bracket. Okay. If you start to write these formulas in the sort of very simple form, in the flat case, you could realize. So what we have is that we have a Lie bracket. Now, if if I have a D dagger, basically, I can equip the space of differential form with a Lie bracket, which would be defined like this. Okay. So in principle, there is sort of general theory. If it's operator of second order, it's a Lie bracket. It's of operator high order, then you will have a higher brackets, etc. So people prove the theorems. You can do it. So, but let's stick to this second order. Then let me just talk about the Chern-Simons, and then I have to finish. So what I need to do is the following. So this is a bracket. Then I would like to evaluate this guy, for example, at the kernel of D dagger, right? So first of all, you can observe that this is a bracket on all differential forms, but this is a basically also will be a bracket on kernel of D dagger. So this bracket is closed under this property. Right. And then what I have to do is the following. So if I take here, let me introduce another funny pairing. So let me introduce pairing between. I'm skipping thoroughly algebra. It's always traces, etc. So imagine I have two collection of forms which lie in the kernel of D dagger. So imagine I write for you A1 is equal to D dagger of xi1.
What's B there on the left? Is that a function or?
Sorry, B? No, oh, it's just collection of forms. It's a 0 form, 1 form, 2 form, etc. So physicists would call it superfield, and you just think as a collection of form. That's all. And then, of course, if you want to know how this bracket looks like, you can restrict to the forms. So if you take A1 to be D dagger of another guy, you can define this actually pairing on M3, which would be xi1 with A2. So you can convince yourself that, first of all, this pairing is well defined. It does not depend on the choice of xi1. You can sort of define it here, putting xi2, etc. So this is actually a good pairing on the kernel of D dagger. Now, if you accept this fact, then what you can do, if you take this section.
It's sort of a linking pairing, yes?
Hmm?
It's sort of a linking.
Yeah, exactly. So if you take this section, for example, and start to write in the pairing, so what do I do is the following. So this is actually, I will get for you the following things. A, Laplace of A. So Laplace operator is just D dagger plus D dagger of D plus pairing of A with A. And moreover, you can show that this pairing is invariant with respect to this bracket. So basically what I did for you in momentum representation is I just rewrote for you the action in this form. So I can write my action if I restrict on the kernel of D dagger as some invariant pairing with respect to this bracket. And then I will have these guys and his invariant pairing. The only problem is this Laplacian, but again, basically, if it wouldn't be this Laplacian, then your perturbation theory looks like invariant pairing contracted with the structure constants. And that's exactly what I showed for you before. And so this is basically a simple way of explanation of this color kinematic thing. So Chern-Simons, and again, I think I will not confuse you more. I could have done for you more examples of theories when things can be done easily, geometrically, but so basically, again, it's not clear how much it will have effect for calculating this big gamma, but at least you sort of look at these structures which people were ignoring so far. So it gives you a new look on these big gammas. Again, I'm not claiming anything for Chern-Simons in particular. For us, it's just a good toy model. We are much more interested in other theories, more complicated. But it seems many of the theories establish this pattern, just much harder to prove. Of course, Chern-Simons is nice that you know this very canonical sort of choice of subspace diagram. So for other theories, you have to do something more elaborate, etc. I think I will stop here. In principle, I had an example of two-dimensional Young Mills, but I think I will not bore you more. Thank you.
I guess we will save the questions for lunch and
For me.
yeah, let's give Maxim another round of applause. We will continue at 2, and the lunch will be served just outside here.